Hi. Good evening, everyone. Thanks you all for being here so late. It has been a very busy day of presentations, so I'll try to be as brief as possible. Just for your information, my dissertation lasted 1 hour and a half. So now I have to squeeze this down in 15 minutes or so. Before even started, I am Edoardo Ramalli. I am from the Information System Group, even if we are also currently going under rebranding, so our name is changing. And my first words wants to be to the committee for this award. This has been a pleasure to be awarded the Florian Daniel Prize. And of course, I would also thank you to all the persons that make it possible, from the department, the university, the PhD program, and all the family and the loved one of Florian that make his memory running all over the years. Thank you so much. Behind this work, another thank you is usually this is at the end, but I know that maybe you are more alive, more awake at the beginning. This award is also to other persons, not just me. So I've been the pleasure to work with several research groups, with the Information System Group here at DAPE, the crack modeling group at the Chemical Engineering Department here at Politecnico, and the CityDang group at MIT. So this is an award also for them, as not just for me. My presentation, my PhD thesis, is entitled Data Ecosystem and Data Science for Scientific Data, where we actually try to do something pretty challenging. And we did something, I believe. So as we know, every day are generated petabytes of data. And these data represent more or less a lot of knowledge that we have today. And the primary use of this data is to use to train, to build a predictive model, because we would like to know the unknown, right? And so this model generation is shifting from a model-centric approach, where basically we built this predictive model based on some theoretical foundation, towards a data-centric approach. So we would like to build this model based on the data that we have. There are so many. But for doing so, we need a lot of stuff, because we need to collect these huge amounts of data, we need to organize it, and it's not just putting in a database just like that, but we also take care of this data, in the sense of we should care about the quality of this data, we should keep them organized in such a way we can extract knowledge from them. In particular, my PhD thesis was an interdisciplinary thesis between, as I said, the computer engineering and the chemical engineering department, where we focus on developing scientific predictive models that are a particular type of predictive model that basically try to replicate, mimic real-world chemical physical phenomena, in particular in a domain that is called the combustion kinetics. And this domain is the one that basically collect combustion data. So basically they have fuels, they burn stuff, they collect experimental data to forecast which are the emission, the pollution, which is the energy that is released. So it's a field that is running all over the years, back right after World War II. And nowadays we are not more interested in diesel or whatever. We are more focused on green fuels like hydrogen, ammonia, stuff like that. So, but since we are dealing with experimental data, so our particular kind of data, there is no plug-and-play solution that we can just apply from whatever is already right there, right? We saw before with genomic data, we need to take care about some problems there. And also in my domain, in the chemical engineering one, we have to take some specific attention. In particular, we need to, and we we developed techniques for data management, data science, and data sharing. The first thing was to understand what's going on, because basically the chemical engineering domain, as I said, it's ancient stuff compared to the web, for instance. So it's stuff that is running for more than 60 years, 70 years. So basically you have this legacy of stuff that you even don't know which is the process, the collections process, the management process of the data that they have. So the first thing was to understand what's going on. And once we finally understood more or less what was going on, we also tried to identify which are the main goals, the main points that we would like to take care. For instance, one of them was heterogeneity. So think about a data that is collected from 1915 and a data that is generated and collected today. So we have to take in account for many decades of data that are very, very different between each other. But at the same time, we cannot get rid of this old data, for instance, because they are precious. To run just one experiment, so just 1 point on a plot, basically they spend thousands of dollars. So we cannot just forget what they did. So, but as I said, you know, we have to deal with combustion kinetics. Combustion kinetics means fuels. Fuels means money. And sharing this data that are used by, I don't know, company to develop the best engine, the best jet fuels. It's a complicated stuff, because we aim to collect all this data from all the research groups around the world in a place, in a data ecosystem that basically was capable of managing all this heterogeneous data, but we had to comply with the intellectual property, with the confidentiality of the data, because data is knowledge, and people, companies, research institutions are not willing to give away research that basically they did. And also we had other problem, like people were not incentivized so much to give away this data, because what about if I just give the data but I don't get anything back? So we also need to account for this social, let's say, organizational data governance problem of this huge repository of data. So it's not just a matter of implementing it, it's not just a matter of saying it's free, it's also a matter of convincing people to actually share precious data. And this is not just blah, blah, blah. We actually implemented it. So the data ecosystem is called SEXPAM. It's under the Polymid domain, so it's actually running and working, hopefully. Still working. And it was a pretty complex work, but it's something that we for sure leave for generation to work on. So we collect thousands and thousands of experimental data. We wrote thousands of lines of code, and so hopefully it's something that will stay there for a little bit. Now that we have this SEXPAM, so this data ecosystem, this giant repository where we can store data, the other problem was to take care of this data. So we cannot just put the data in a place and say, oh, that's fine, that's all I can do. We have to quality of this data. So we also took care about some data quality dimension, for instance, the completeness, because sometimes they provide, I don't know, something, a number, but we don't know if this is in meters, miles, or stuff like that. Or also sometimes they put that the weight is something that is negative, and we know that it's pretty, you know, difficult to have the weight that is negative. But for them was a meaning just the concentration of a species was not was not detected by the sensor. So, you know, we have to deal with this stuff. But the most important thing for us was to focus on uncertainty. So basically we have multiple, as you can see in the plot on the left, we can have, for the same experimental setting, we can have multiple people that are doing the same stuff, doing the same experiment. And since we are dealing with real world data, so we have the experimental uncertainty that we have to deal with, right? We don't know which is the truth. So which one is the real data? All of them? None of them? We don't know. But uncertainties comes in play when we have to compare the experimental data with the model that we have to assess if the prediction are good or not. If basically we don't have the wire or bars, we cannot say if we are inside the error range or not. And in our, we have like, I believe, hundreds of thousands of experimental data points, but less than 10% of them have uncertainty. And so we tried to figure out a way to put uncertainty when we don't have it. And we basically used knowledge graph embedding model because we basically try this thing that if maybe the calibration of a sensor is incorrect, maybe if this experiment is done systematically by a research lab, maybe also the experimental uncertainty somehow is related, because if the error is propagated all over the experiments, maybe we can do something like that. With this knowledge graph embedding, where we built this knowledge base correlating the experiment with some metadata, for instance, the author of this experiment, where it's published, when it's published, which is the instrument of this experiment. We try to guess which is the uncertainty when we don't have. Actually, it's something that works. So now that we have the data ecosystem, SciExpand where we store the data, now that we took care about the quality and the uncertainty of this data, the last step was to deal with how we can leverage this new knowledge use organized knowledge in such a way we can automatically build a new predictive model more or less automatically. And as I said here, the field is running for many decades, and if you ask two different research groups if model 1 or model 2 is better than the other, you can get a very, very different opinion. So determining which is the valid model evaluation strategy is something that is quite challenging. And so what we did is to try to define a systematic, objective, and automatic methodology to validate a scientific predictive model in the combustion kinetics field. And so we tackle all these aspects. For instance, we did something about assessing which is the coverage of the data set. So it's not just a matter of saying I have a bunch of data and I assess this data against this condition, but it's also a matter to validate the validity of the validation, in the sense that it's not just a matter of saying, okay, I did 100 tests, but I want to be sure that these 100 tests are different. They cover as much as possible all the different configurations in real world domain. And so I don't want to go into details, but basically this is the publication if you're interested in, but we tackle all these aspects in such a way we can propose a methodology that is standard, objective, and automatic. So this is just my last slide. To sum up, so this was an interdisciplinary thesis where we proposed to extract value from this large amount of scientific data in such a way we can do some scientific predictive model generation. We design an and implement a data ecosystem. We identify which is the overall process, which are the data management aspect that we should take care of. We suggest how to guess which are the missing uncertainty for the experimental data. And finally, we propose a systematic objecting and automatic model validation. We did also a bunch of other stuff related to data ethics, adaptive sampling, networks, but time is up. So thank you all for your attention. I'm glad if you have answered to take them.